Hi everyone, my name is Felix, and I'd like to talk to you today about joint work between myself and Jochen Koeneman as well as Justin Toth. So before we begin, let's review some cooperative game theory. The setting is a finite collection N of players, where any subset S can collaborate to generate revenue. More formally, we have a pair N and nu, where nu is a set of players, say from 1 to n, and nu is the characteristic function, which is real valued and defined over all subsets of players. We can think of nu of S as a revenue generated by coalition S. Some common questions we can ask in cooperative game theory are, what sort of coalitions will form? Or how will the total revenue be allocated? Going down that train of thought, let's define an allocation as a real vector where the sum of entries is equal to the total revenue. One way to divide revenue is to look at the subset of allocations where each individual player is allocated at least as much as they can earn by themselves. Let's call those imputations. Now let's introduce the B-matching problem. We have a graph G, edge weights W, as well as a vertex incidence function B. Our goal is to find a set of edges M maximizing the sum of weights such that every vertex is incident to at most a given number of edges. Notice when B is equal to 1 for all vertices, this is just the matching problem. In the figure below, I indicated a maximum 2 matching when the weights are uniform. Alternatively, we can talk about non-simple B matchings, where we're now able to select a multi-set of edges, but everything else stays the same. Again, in this figure below, I indicated a maximum non-simple 2 matching when the weights are uniform. I've also explicitly chosen the edges to be parallel edges to stress the fact that we can choose a multi-set of edges. Now, what is a B-matching game? To start, we have an instance of the B-matching problem, and our player set are the vertices. We also define the characteristic function, say nu of S, is the weight of a maximum weight B-matching in the graph induced by S. For instance, in this coalition, in this component, the maximum B-matching is 4, and in this component, the maximum B-matching is 2. So let's work towards a definition of a fair allocation. Let's define the excess with respect to allocation X and coalition S as how much we allocate that coalition minus what they can earn by themselves. Let's think of that as the satisfaction of a coalition with respect to X. As a revision, the imputations are precisely the allocations with non-negative excess along all the singletons. Generalizing this idea, let's require the excess to be non-negative over every single coalition, and those allocations define the core. So let's review some facts about the core. For one, stable matchings with payments, which is a variant of the stable marriage problem, they actually correspond to core allocations. The core is non-empty, always non-empty in fact, when the underlying graph is bipartite. We can actually say a little bit more. So the core of a combinatorial optimization game is non-empty if and only if the fractional LP of the underlying problem has integral optimal solutions. In the specific case, the bipartite B-matching polytope is totally unimodular, and therefore is integral. Unfortunately, the core can be empty, even for one-matching games. And let's look at this trivial example of a triangle below. Suppose we want the coalition U and V to have non-negative excess. That means we have to allocate all of our revenue along U and V. But then W doesn't get anything, and one of the two other size 2 coalitions involving W is guaranteed to have negative excess. So this core suffers in that it doesn't always exist, and even when it does, it's not unique. So what can we do about that? The idea is to maximize the satisfaction among the worst case coalitions. This LP below formalizes the idea where among all allocations, we're going to maximize the minimum excess. So suppose we've done that already. Why should we stop at the worst case, guys? Let's fix the worst case coalitions, then try to maximize the second worst case. Fix those, try to maximize the third worst case, and so on. More formally, let's define the theta vector as the exponential size vector where the entries are the excesses sorted in non-decreasing order. The nucleolus is the unique imputation which maximizes the theta vector lexicographically. So some theoretically relevant facts. The nucleolus always exists, is unique, and when the core is not empty, nucleolus belongs to the core. So the nucleolus has some very nice theoretical properties, but how can we actually compute this? The idea is to solve a sequence of recursively defined linear programs, and this scheme is known as the Capellowitz scheme. So we're going to start with LP1, which is the exact copy of the LP we had earlier. And suppose we solved LPK. We say a coalition is tight if for all optimal solutions epsilon k of LPK, the excess is tight. Then you can define LPK plus 1 recursively by fixing all the new tight constraints. So transitioning from LP1 to LPK plus 1, we fixed all the excesses for the coalitions that were previously tight. And then we're going to maximize the worst case excess among all unfixed coalitions. Now, each LP has an exponential number of constraints. However, at least one coalition is added to JK for every K. So in the worst case, we solve an exponential number of LPs in this scheme until the solution is unique. So even though the Capellowitz scheme is not efficient, in the sense that it doesn't terminate in polynomial time, we can still use it to characterize the nucleolus. It's worth noting that there is a variant of the Capellowitz scheme called Maschler scheme, and this actually guarantees termination after a linear number of iterations. Now we're finally ready to state the main results. And that's deciding whether an allocation is equal to the nucleolus of an unweighted bipartite 3-matching game is NP-hard, even in graphs of maximum degree 7. As an easy corollary, computing the nucleolus of a bipartite B-matching game is NP-hard, even when B is at most 3 and the underlying graph is sparse. We also have some partially positive results. So given a bipartite graph G, edge weights W, and B at most 2 for every vertex. Let's let K be a universal constant. Suppose B of E is 2 for every vertex at one side of the bipartition, but BV is 2 for at most K vertices in the other side of the bipartition. Then we can in fact compute the nucleolus efficiently. On the other hand, if B is equal to 2 for all vertices, we can compute the nucleolus of the non-simple B-matching game efficiently. Before we delve into the details of our proofs, let's talk about the related work, beginning with one-matching games, or otherwise known as matching games. In 2003, Kern and Polysma posed the question of computing the nucleolus as an open problem. In 2008, Deng and Fang conjectured this problem to be NP-hard. 10 years later, my co-authors as well as Konstantin Pashkovich showed that actually we can compute the nucleolus efficiently and disproved the conjecture. We know a little bit less about B-matching games. In 2010, Botteni and co. gave a polynomial time algorithm to compute the nucleolus, and the underlying graph is bipartite, as well as one side of the bipartition is restricted to BV equals 1. In 2018, Biro and co. proved that testing core membership is NP-hard, even in bipartite graphs, and B is 3 with uniform edge weights. 1 year later, the same authors showed that testing core non-emptiness, and therefore computing nucleolus, is also NP-hard, even when B is at most 3 and the edge weights are uniform. However, this proof uses a gadget graph with many odd cycles, and it thus doesn't hold when the underlying graph is bipartite. Given what we know, this partially positive results for bipartite graphs, and the fact that hardness result depends on lots of odd cycles, this seems to support the plausible conjecture that the nucleolus is efficiently computable when the graph is bipartite. Surprisingly, our work answers this in the negative. Let's delve into some details of the hardness proof. Before we begin, recall that the cubic subgraph problem asks whether an arbitrary graph contains a subgraph where every vertex has degree 3. This was proven to be NP-hard in 1984 by Plesnik. We'll also introduce a variant of this problem, where now we're asking for a subgraph where every vertex has degree 3 except for two vertices of degree 2. We show that this variant remains NP-hard even in bipartite graphs of max degree 7. Our proof builds on Plesnik's ideas, however it requires significant innovation in the gadget graph. It also relies on a piece of graph theory I'll paraphrase below. Let X be a regular subgraph of some graph G, and Y a highly vertex-connected subgraph of G. Either X contains all the vertices of Y, or it contains none of them at all. Now, in the interest of time, I'll omit the details of this hardness proof. Let's talk about reducing this variant to nucleolus computation. Let G be an instance of 2 from cubic subgraph, say a graph we have over here. Let's create a gadget graph G star by adding a K33 to every vertex. What I mean by that is, for every original vertex U, we'll add 5 new vertices and connect them in a way that results in a K33 subgraph. The nucleolus of the unweighted 3 matching game on G star is some specific allocation if and only if G does not contain a 2 from cubic subgraph. Let's make some remarks about this gadget graph. For one, it has a perfect 3 matching. 2, it's going to remain bipartite, and therefore the core is not empty. Recall that's due to the fact that the fractional B matching polytope is totally unimodular and thus integral. We also remarked that Biro and co. use the same gadget for their hardness of core separation. Their proof was that some allocation resides in the core of the B matching game on G star if and only if G has no cubic subgraph. So our proof differs in that we're concerned about specific allocation being equal to the nucleolus if and only if there's no 2 from cubic subgraph. More specifically, the uniform allocation, which assigns 3/2 to every player, is equal to the nucleolus of the 3 matching game if and only if the original graph does not contain a 2 from cubic subgraph. So how would such a reduction work? Well, let's let X star and epsilon k be an optimal solution to each LPK of the Capellowitz scheme. I've typeset that below to remind us what that is. If there is no 2 from cubic subgraph, then epsilon 1 is 0, epsilon 2 is 3/2, and the uniform allocation is the nucleolus. If there is a 2 from cubic subgraph, then epsilon 1 is 0, and the uniform nucleolus is not, the uniform allocation is not optimal in LP2, and therefore it can't be the nucleolus. So let's first consider the case when there is no 2 from cubic subgraph. How could we show epsilon 1 0? Well, for one, it has to be at least 0, just because of core non-emptiness. It's also upper bounded by the excess of any of these K33 coalitions. Well, we realize that each of these K33 excesses is non-negative, and when we add them up, we get the excess of the grand coalition, which is 0. Therefore, each of these K33 excesses is 0 as well, and that shows that epsilon 1 is 0. We can in fact show that the only coalitions fixed in LP1 are the union of K33 gadgets. Now, moving on to epsilon 2 is 3 over 2. Since we have a perfect 3 matching in the gadget graph, epsilon 2 is upper bounded by the average allocation to each individual player. We can also show that the minimum excess coalitions, which were not previously fixed in LP1, contain the singletons, and so therefore epsilon 2 has to be equal to 3 over 2. This uses the fact that G does not contain a 2 from cubic subgraph, so that's where this assumption plays its part. In the case when we do have a 2 from cubic subgraph, the proof is very similar. Epsilon 1 is going to be equal to 0 again, but we're now able to construct an explicit allocation that's going to be feasible in LP2, but has strictly greater objective than the uniform allocation. Let's also talk about some positive results. The problem with the Capellowitz scheme is that there's too many constraints. So why don't we just remove some that are not necessary? If the remaining constraints are polynomial sized, then the nucleolus can be efficiently computed. For instance, if the core is non-empty and there's some maximum B matching, the graph induced by S, such that the matching is disconnected, then the constraint corresponding to S can be omitted. For instance, let S be the grand coalition of all players. In this example below, we can omit S because it's disconnected, and therefore any maximum B matching is going to consist of a B matching on one component, direct sum with a matching on another component. First, let's talk about simple B matching games, where BV is 2 for all V on one side of the bipartition, but BV is 2 for at most K vertices on the other side of the bipartition. This is an extension of the work from Bateni et al., where they required every vertex to have BV equals 1 for the other side of the bipartition. It's not hard to see that the largest connected component in a B matching has cardinality at most 2k plus 3, which is a universal constant. Then we can run the Capellowitz scheme over all subsets of size at most 2k plus 3. And this is going to be a polynomial. Now let's consider non-simple B matching games. Suppose B is equal to 2 for all vertices. Then we can show that there's a maximum non-simple B matching consisting of only parallel edges. To illustrate this idea, in the 4 cycle, the maximum non-simple B matching could consist of all the edges, or we could fold every other edge on itself to get a disconnected non-simple B matching. Therefore, it suffices to run the Capellowitz scheme with n² constraints between all pairs of vertices. In conclusion, computing the nucleolus for simple bipartite B matching games when B is at most 3 is NP hard. Fortunately, when B is at most 2, there are efficient algorithms to compute the nucleolus for special cases. The natural question to ask following our work is whether we can efficiently compute the nucleolus in general graphs when b is at most 2. It would also be interesting to explore combinatorial algorithms to compute the nucleolus. Thank you for attending my talk.